Are you ready? Okay.
Okay, so I hope everyone is well fed, well coffeeed up, and alert and awake for the second lecture by Darren Croton. He's going to talk a little more about galaxy formation models. So, Darren, go ahead.
All right. Thank you for that. Hi, guys. Hope you're having a great day there and that you've caffeinated appropriately. It's always tough to give the last talk of a day, so I'll try and keep you involved and awake if the caffeine doesn't do it for you. All right. So I'm showing this nice movie in the background here. I hope it's not coming through too jittery for you there. Does anyone know whether this is a simulation or real data? Can anyone guess? Maybe we'll have a show of hands. Who thinks it's a simulation? Put up your hand. No one put up their hand? You did it? Okay, great. Who thinks it's real data?
Most people.
The whole room. Okay, good stuff, guys. You win the prize. You don't win cash. You win the satisfaction of being able to tell the difference. This is, of course, real data. This is the 2DF Galaxy Redshift Survey. It was a fly-through made. Now, one thing I want to point out, you can hopefully see the galaxies here, right? These are not the actual galaxies that the survey imaged because the survey was a redshift survey. So they just took positions and properties, but not images of the galaxies. The galaxies put into this movie are color matched from Sloan, I think. So they're cheating a little bit. The other point to make with this movie is that the galaxies are about, I think, a factor of 10 to 100 times larger than what they would actually appear to be. If you put the galaxies into this movie, their actual size, you wouldn't see anything. You'd see these tiny little dots. Okay, so to see the galaxies, you have to make them like 10 to 100 times larger. So just some illusions there in the marvelous field of astronomy visualization. But real data. All right, so let's go back to, can I advance my slides? Here we go. All right, good. Let's recap a little bit what we were talking about yesterday. I know that you're getting a heap of information in this school, and I'm wondering who feels like they've reached their saturation point already? All right. I know what it's like. You go to a 5-day conference and after about day 3, you're thinking my brain's going to explode. I can't hold any more information in. So let's just go back over what we were talking about yesterday. So we're talking about galaxy formation models, simplified models, ways to represent the global properties of the population of galaxies in the universe. And to do this, we broke the problem into 2 parts, the skeleton and the flesh. And the skeleton was the dark matter, which represents most of the mass in the universe. So we can separate this out and simulate that separately with a very large n-body simulation. And then the flesh is the baryonic physics, of course. And so we don't want this. This is Hubble up above the Earth. We destroy Hubble. Instead, we want to go to a supercomputer. Remember, this is our laboratory in which we're going to do our experiments. So we take images and take spectra of real galaxies, but in order to understand them, we need a theory, we need to model these, and in order to do that, we need to move into the wonderful world of nonlinear physics. The only way with systems like our universe and galaxies is to use a supercomputer to do that. All right, so we took the cosmological model, which is predominantly dark energy, but as from the point of view of the mass component is made up mostly of dark matter, as I said, and some atoms. And we ran an n-body simulation. Here is the Millennium simulation, but you could run multiple kinds of simulations with different cosmological models if you thought that the cosmological model that's currently favored is not the right one. And then we ran our galaxy model on top of that. So remember, the galaxy model is a simplified representation of two components, or two aspects really. It's the reservoirs of baryons, the main reservoirs of baryons, which really are hot, cold, gas, and stars, with some black holes and maybe some ejected gas thrown in. And then the physics of galaxy formation, which we represent with simple equations, differential equations, that describe how the baryons move between those reservoirs. Now, to inform those equations, we use things like the observed phenomenology of star formation and supernova, blowing gas out of galaxies. We sometimes use more sophisticated simulations to infer the behavior, reduced down to simple equations. But whatever we use, we have full control over. We have to parameterize these relationships of how baryons move between the reservoirs, because we don't really know the efficiencies and we're trying to compensate for a lot of unknowns. But those parameters still should be meaningful, even if the exact values are not something to worry about in too much detail. So the parameters still should be meaningful. If you have an efficiency of star formation parameter, then the number that you're putting into your model should be reasonable. It should be of order 5, 10%, 2%, something like that. If you need 200%, you've done something wrong with how you set up the model. All right, so we're coupling a numerical simulation to an analytic simulation, numerical simulation of the dark matter, which only has to worry about gravity, and an analytic simulation that tries to represent everything else in the universe, all those messy baryons. And so we come back to our n-body simulation here. We use the merger trees from the n-body simulation to track the evolution of the halos, and coupled to that, then the analytic model of galaxies evolves on top. And at the end, we get a galaxy population. And that galaxy population has a number of properties, and those properties are hopefully things that we can compare to the real universe. So for example, this galaxy population here in the Millennium simulation, coupled with the SAGE semi-analytic galaxy model, at redshift 0, you get out about 20 million galaxies at the end. And those galaxies have properties like the stellar mass, the star formation rate, the luminosities and different filters, the disk sizes, the outflow rates, the metals, all these different things, right? So you can do all your favorite statistics on that. And so here I'm showing the K-band luminosity function as a function of its abundance. The abundance of galaxies is a function of their K-band magnitude, which is called the K-band luminosity function. And on the right-hand side, I'm showing the color magnitude or color stellar mass diagram. And remember that I emphasized that these are calibration plots. What's really important here is what we needed to do in order to reproduce the observations. So I talked about two different modes of feedback, supernova and AGN, and how the models reveal that to match the observations, supernova really only has to be efficient, or can only be efficient at its low mass end, because the supernova rate depends on the star formation rate. Once the potential well gets deep enough so that these massive galaxies that live in those massive halos, they still have supernova going off sometimes, unless they're quenched. But even if they do, the potentials are too shallow to get the gas out. Okay, so the behavior, the quenching behavior due to supernova is not really very effective. And then converse for the AGN. AGN are incredibly powerful. They have enough energy to get the gas out of those deep potential wells in those big clusters and the large groups. However, in the low mass population, the low mass galaxy population, the black holes never get large enough in order to drive the kinds of jets that AGN are typically seeing, right? So this is real physics that we see in the universe. We're not just making stuff up here, even though we have some freedom to choose how to implement the physics that we see. And again, we have to parameterize the efficiencies and the relative importance of those processes. So this is exciting. So we can go and build a galaxy population and explore it like we're exploring real data and look at the consequence. All right, now I was going to throw money at you if I was there. Unfortunately, I'm not there, so you'll just have to ask Karen for the big bucket of cash sitting above you. She can pull that chain and it will come down on you. So this was the challenge. What's that? All right, so this was the challenge that I normally throw out there, that when I come and we do these tutorials, I typically give you a challenge where the model, can I just ask, I'm getting an echo here now.
Hi, Darren. I think there's the connection maybe.
Did you change something?
Maybe a little bit jaggy, but we can still hear you.
I'm not sure if something changed, but that's much better. Actually, I still hear the echo. All right. Anyway, let me move on. So the challenge that I give you is that even though I showed you I can reproduce the redshift 0 stellar mass function and luminosity function, which is the black line here, if we look at this model and what it predicts for the mass functions at higher redshift, it gets it completely wrong. So the data here are the dashed lines. Different colors represent different redshift ranges indicated in the legend here. And the model is the solid lines, and we massively overpredict the low mass population of galaxies at high redshift, and we underpredict the abundance of high mass galaxies. So, you know, this is a big problem. And you could say, well, this model's failing miserably, but actually the model is doing exactly what it's intended to do. In the lambda CDM cosmology, where hierarchical growth determines how structure formation evolves, the little things form first. And so it's no surprise that we're forming little galaxies in little things at high redshift. And the big things form later. And so the fact that we get the overabundance of small galaxies and underabundance of high mass galaxies is exactly what we should expect from this model, but it's not what we see. And this highlights a decoupling of the baryonic physics and the baryonic evolution from that of the dark matter. And you could kind of just rationalize this out without a model, but it's nice to explicitly see it. I don't see this as a failure of the model per se. It's an opportunity now to go and explore what kinds of physics would give you the decoupling between the baryonic evolution and the dark matter evolution, compared to what you see from lambda CDM. So you can go and explore that now and hopefully get some insight into what the critical physical aspects are that would shape the actual galaxy population. Now, it may be that the observations are wrong and we're under-predicting or over-predicting the mass function primarily because the observers are missing galaxies at high redshift. And that might be true as well. So you have to take everything with a grain of salt and not too seriously, and not forget why you're doing this. You're doing this to gain insight into the galaxy population and what shapes its evolution. And whatever tools you can bring to bear on that problem are good. They're good tools. But as I said yesterday, never think that what you're doing with your models is producing the real universe. Or with Illustrious or Eagle, the most beautiful hydrodynamic simulations, none of these are the real universe. They're just imperfect representations. And their goal is to try and understand the real universe. All right, and this just emphasizes that point here, that the model is only as good as the questions we ask. Okay, and for systems of infinite levels of complexity, our model can never be correct. It's never right. Okay? There's no such thing. No one can build a model of a person and claim that from that model, they would be able to reproduce an actual living, breathing person. Okay, but that doesn't mean the models are not insanely valuable to understand people and to help them and predict their behaviors and so on. Okay, and that's what we're trying to do here with galaxies. All right. Okay, so in this lecture, that's the recap. If there's any questions, I'm happy to take them. But what I'm going to do in this lecture is show you some examples of what I think are good usage cases of the models, okay? Or at least instances where the models have been helpful in gaining some insight into the real galaxy population. But before I do that, I just want to sidestep to something that really is new for you guys, especially the students here, and maybe at least it's new in terms of your careers and how you will do science. If you go back 20 or 30 years, science wasn't done this way. So the impact of the Sloan Digital Sky Survey database, right? The impact on science has been enormous. And there's been this slow realization that data access is insanely powerful. If you go back into the 70s and 80s, people would go and collect their data, right? Or run some simulation. They would store it on their disk and they would sit on disks in their office for 10 years. Why would they share that data with another team that could go and scoop all the exciting science results? And so they would just sit on it and they would gradually release their papers as they got students to work on it or whatever. Okay, this has totally changed with the internet, with cloud services, with massive data sets that are insanely rich, richer than any one person or group can mine in a lifetime. And Sloan pioneered this, but they weren't the first. For example, with simulations, there was the Hubble volume simulation and the GIF simulations before the Millennium simulation. And these were accessible to the community. If you contacted the authors, they put them online so you could download the data and use it yourself for your own science. So I'm going to talk a little bit about my experience with this. Just to point out though that I think we're entering an age where the vast majority of papers on the archive and in the published literature will be done with archived data, not data that you will go to the telescope yourself and collect. Okay, the vast majority. We may already be there. So get used to this. Okay, get used to accessing the data through the internet, through a browser. So I was inspired to put my data online because I did my PhD at Munich, and so that's the home of at Max Planck Institute for Astrophysics, and that's the home of the Millennium simulation. And as we were running the Millennium simulation and building the models, we put them online into this database called the GAVO database, German Astrophysical Virtual Observatory. And some of you might be familiar with this and have even used it. It was pioneering from the theoretical point of view. And what you do is you come into this little box here and you type an SQL query to query the database. And the database held the semi-analytic galaxy catalogs and the HALO catalogs. Okay? And people would email me all the time because my models went into this. People would email me all the time and say, what's the SQL query to do blah, blah, blah? And I would respond and say, I have no idea. I don't need to go to this database to get my own models. My own models are on my laptop or on my computer. I don't need to put in an SQL query. So I couldn't help them. I had to send them on to someone else. But it made me realize that a lot of astronomers don't know SQL. And SQL is one of the most unintuitive programming languages for an astronomer. So can I just have a show of hands, right? Who here programs in C? Right? What about Python? All right, can I be so bold as to ask Fortran? Oh God, no! All right, what about SQL? Who's coded in SQL? Yeah, a pioneer down the back. You'll get the .com job, okay, and earn lots of money. And maybe that money can be put above all the students here and it can rain down. All right, yes, exactly, all right? And the first time I went to write something in SQL, I had to Google how to do a for loop in SQL. There's actually no for loops in SQL. The logic and the structure is totally different. And I realized from getting all these emails, especially from observers who wanted to use some mock catalogs to compare to their observations. And they didn't want to have a hard time of it. They didn't want to spend the same amount of time they spent on writing their paper as to fold in some theoretical data. They just wanted it to be easy and simple. And if they had to learn a new programming language, it wasn't. Now, down the bottom here, you've got some buttons on Gavo, and these give you examples of SQL queries. So they try and make it easy for you. But if you want more complicated, if you want to pull more complicated data out, you have to, you're kind of on your own. You have to get some help. So this inspired me that there must be an easier way to get access to data. And can we build something that complements Gavo? Right, so this is Garbo, right, as a representation in a flowchart. So down the bottom, you've got a simulation database. So that's where the different data sets sit. And then you've got this SQL query front end that you do through the web browser. And our goal, so this was building the theoretical astrophysical observatory. Our goal was to still have the simulation database, you have to have that. But instead of having an SQL data query interface, we had a web form data query interface. And I'll show you this in a minute, okay? So you didn't have to code. It was just drop-down boxes and selecting properties from lists, okay? And the SQL was written by the system behind the scene. So you never had to write or even, but we didn't need to stop there. Taking a lot of the complexity out of it for the user. We added a number of tools on top of this. So Tau can build SEDs and put filters down on top of those SEDs. And we can do that because the simulation database has all the historical information of every galaxy. And so what do you need? I mean, I think Claudia's probably gone over this. If she hasn't already, she will. Right? To build an SED, you need the star formation history and the metallicity history, basically. And you need to be able to track that object and all its progenitor parts back in time. And you can do that easily with the database. So with that and some assumptions about stellar population models and so on, we can build SEDs and give filters. We can build light cones and we can make images. Okay, and ultimately these can be coupled together into sort of a pseudo telescope simulator. So I don't think I'm going to go through this. These are just some of the details of how we would do, how we would do it. For example, reconstructing the star formation histories of galaxies and so on. But let me, well, here's a mock light cone that Tau builds. And we can pick some interesting objects in that light cone and build an image. So here's an image using an image package that's coupled behind Tau. So you can just get these. Again, no coding needed. But let me just, hopefully you can still see what I'm doing. Can you see this page here? Yeah, actually, let me move it over to here. All right, so now I can see what's happening. All right, so this is the Tau entry page. And if we go to new catalog here, once it loads, or maybe I should have just done this. Gil?
Hi, Darren?
Yeah, can you hear me?
Yeah, but we're only seeing the that you have there.
Can you see the new catalog page?
No.
No? Oh, hang on. Let me do this. I know how to do it. Sorry, guys. Here we go. How's that? Yay. All right. All right. So you would come into Tau. Oops. Oh, sorry, I just did something bad. So you would come into Tau at a page like this. All right. And then you would click on New Catalog up there, and you would come to a page here. Okay. And this is where you can make some choices. You can build a new catalog. You can load a catalog you've done before. You can load some telescope survey presets. So for example, if you wanted Sloan, a mock light cone with Sloan. Okay, so this is where you do the fun stuff. So remember that box with Garbo that you had to go and type your SQL query in? So this sort of mimics that. So here we're selecting a box. What simulation do we want? And the nice thing about Tau is not only do you get to choose from just one simulation. The Millennium is primarily the simulation that that Garbo has, but you can pick from a whole bunch of them, like the multi-dark simulations or a different galaxy formation model on that simulation. And we're currently putting lots of models in, and you can select what version of that model. You can sub-select the box size and pick the redshift that you might be interested in. So let's just stick at redshift 0. And here we have all the properties that this galaxy formation model predicts. So we have the stellar mass, the cold gas mass, the black hole mass, for example. We have additional things like the classification. Is this a central or a satellite galaxy? The scale radius, the heating rates of AGN. We have the halo information, virial masses, the spins, and so on. We have some XYZ positions and so on, right? And so you just add those to what you want. I'm just going to add them all. You can choose to apply the SED module. And just because Claudia might be there, let's pick a Mariston Salpeter IMF and stellar population models. All right, let's pick some filters. So you can see if I, how many different filters are here. Galax, Hubble, Herschel, Spitzer, HST, more HST, Johnson filters, Keck, blah, 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 music, right? We have 100 and something filters, but let's just pick the Sloan ones, and we're going to take apparent and absolute magnitudes. Okay, we can pick to apply a dust model on top of that. So Calzetti or slab. Now we can do our selection, right? How do we want to cut our catalog? So let's just cut by stellar mass. And notice that the units here are 10 to the 10 solar masses. So let's take everything above 10 to the 9, which would be 0.1. Okay, so if you're old, like me, you might want a text file, but you can have a FITS file, or you can have HDF5. So you can get your data back in whatever format you want. And then you just go summary and submit. And so my first catalog, which I spelled wrong. All right, and so here we have box, millennium. We can look at what we're selecting. And now we would just hit build mock, right? And it will create the SQL query and send that off to a supercomputer and build it for you. And this is my history page with a whole lot of mocks that I've made. And when that's ready, and it might take an hour, 20 minutes to make, or it might take 5 or 6 or 7 days, depending on how many galaxies. Sometimes you can have 100 million galaxies in a catalog. It might take a long time to do the SEDs for them and everything. But when you're ready, you just come back, and I'll just come to this one. This is one I made before. And you can download over here it as a tarball. You can rerun it. You can load it as a template. You can do a whole bunch of things. All right, so the cool thing is, though, that instead of just doing a box geometry, you can do a light cone. And now you get to pick your R 20 degrees by 40 degrees and a declination of 40 degrees up to 60 degrees. Let's do this between redshift 0 and redshift 0.5. See, someone's registered already. Thank you so much for that, kind sir. All right, so how many light cones do you want? What are we doing here? Why did we get an error? Light cones, how many light cones you want? Then you're going to go and select your properties again. And you would do the same thing. You would come through. I haven't done a selection here. So let's select galaxy masses greater than 10 to the 10. All right. And now I see my catalog is a light cone geometry, same thing. Okay. And so now I've got a light cone, just like the one I showed you. All right. And so again, there's no programming required. And the cool thing is that you can generate exactly the same catalog, but with different galaxy models. Or you can generate the same model, but with different simulations. Okay, whatever combinations we have in the database, you can do. You can get it in exactly the same format with the same H units, the same other units for stellar mass units and so on and so forth. And that way, hopefully it makes it easy to compare different models. And if you're an observer, there's no programming required and so on. So this was our contribution to it. We're trying to get data in there. If you have some theory data you want to put into Tau, please let me know. I'd be happy to do that. All right. So that was just a sidestep to Tau. And from that, you can get data to use in your, I didn't even go over the image generation stuff. But you can get data to use in your science, right? So let's actually talk a little bit about some science now with these galaxy models. All right, So what can semi-analytics tell us about galaxy formation? Very important question, because if they can't tell us anything about galaxy formation, then there's not a whole lot of point, and I've wasted about 20 years of my life. Which may be the case, but who knows? All right, let's ask some questions. What's the time? 1:15. All right, let's go through about 20 minutes of examples. All right, so here's one. Here's a question that I had that I don't think we still know the answer to. So black hole growth, okay? So how do black holes primarily grow? Is it through mergers, all right? Or is it through secular evolution? Now, when I say grow, I mean that the gas that's around, that's in a galaxy, in order to get down to the black hole, it has to lose angular momentum. And that angular momentum loss primarily only happens through very violent or very extreme circumstances. That angular momentum has to be transported out. And in equilibrium, the gas will just sit in the galaxy and not enough will be driven down onto the black hole. All right. So mergers primarily are the dominant mechanism through which people think black holes grow. So during the merger, some fraction of the cold gas is driven onto the black hole. And most semi-analytic models work under this assumption, or have until the last few years. And so here's a very simple model. This is basically the model that we use in SAGE and that a lot of other people have used. So when a merger happens, the change in the black hole mass is equal to about 0.3. Forget about MR here. This is just a modulating factor. This is about 0.03 of the cold gas in the disk. All right. So if you've ever seen these simulations or even observations of mergers, they're very violent, okay? Gas going everywhere, stars going everywhere, enough to totally destroy a disk. And in that process, enough angular momentum is transported out that drives cold gas in, and some of that gas gets captured by the gravitational potential of the black hole and causes it to grow. And remember that these are cosmological models, so the very short time scale physics, like 1 million year and shorter, even 10 million year, we're not worrying about that. We're just looking on average over the scale of 20, 50, 100 million years. When that merger happens, how much gas will get down? Okay, so this is a simple model, and it actually does remarkably well. So here is the black hole bulge relation, and I showed you the observational version of this plot yesterday that we calibrated against. We used a phenomenology there to calibrate against. And so this is the data from Haring and Ricks, and we don't have a whole lot of points, but you can see this correlation here between these two components of the galaxy. And with this merger-driven growth model, okay, we don't do too bad. We see a similar correlation. We don't have data down here in the low mass regime. So this spread here is probably fine. Maybe that's a prediction. Okay, so that's how we typically build our black holes in the model. And black holes are very important because they factor into things like our quenching, our radio mode feedback, and jets and all that sort of stuff. So we need a good black hole population, or at least one that looks like the observed black hole population as a starting point. Okay? However, right, is this merger driven? Yo? Sure, go for it. Yes. Yes, we can. Yeah, the Milky Way actually has a very underdense black hole. Or sorry, not underdense, undermassive black hole compared to the relation. But when you look at the population of Milky Way type galaxies in models such as this, you definitely get those sorts of galaxies come out.
No, actually your scatter is good because in the other tight relation, the Milky Way off.
Yeah.
That was always, while if you have simulation that reach larger,
Yeah.
you can find it because it, yeah.
Yeah, and actually, I won't talk about this, but we wrote a paper a number of years ago asking the question, is the Milky Way a typical L-star spiral galaxy? And it's probably in particular. color magnitude diagram. So let's imagine you were in another galaxy building a galaxy population like we do, a Sloan type population, and then you put the Milky Way into the color magnitude diagram. Would it be a blue cloud galaxy like we often think of it as? And it's not. It's actually in the Green Valley. The Milky Way is a Green Valley galaxy. And Green Valley galaxies have kind of unique properties, or at least we think they're a distinct population that are quenching. So anyway, that's for a different talk. But an interesting result. That's a paper by Much et al., M-U-T-C-H. All right, so this is the model that we typically use, okay? Great. Nothing spectacular here. This was a calibration plot. So like I was saying yesterday, don't be impressed by this or anything. We set the model up, so it gave us a good black hole population. But the question is, what if we changed the growth channel? So we turned off merger growth and we introduced a secular growth. Now, what do I mean by secular? For those who are not galaxy astrophysicists, right? Secular just means that you have a stellar disk and you have a disk instability. You have an instability in that disk and a bar will often form. And what happens is when the disk becomes unstable, it will want to reorient the distribution of mass to become stable again, okay? And in that process, a bar often forms. You might get a starburst, and there'll be a redistribution of the stars and the gas, and angular momentum will be transported outwards. And so let's build our black holes now through secular-driven processes. So as the disk becomes unstable, some fraction of the cold gas is dragged inwards and accretes onto the black hole. So we'll totally turn off growth through mergers. So merger-induced growth, that's gone. And now we have a Toomre criteria that measures the stability of the disk in the model at each time step. And whenever it becomes unstable, let's just take 1% here, 0.01 instead of 0.03 we had before. This is a parameter that I just chosen, but it's again in the ballpark of where we would roughly want to be. 1% of the cold gas goes on to the black hole. Okay? So in that process of redistributing the mass, some of that will actually get redistributed inwards and end up on the black hole capture. Okay? So it's plausible, right? And what we're looking for here is, does this make different predictions about the galaxy population? Because if it does, we can go out and observe, look at particular things, and maybe we'll be able to distinguish between what the dominant black hole growth mechanism is, right? So here's our merger-driven growth, and that's our black hole bulge relation. And this is what we get when we turn off merger-driven growth and turn on secular-driven growth. So this is the disk instability-driven growth. Now, it looks different. So Claudia, unfortunately, your scattered relation goes away. It's a bit tighter, okay? But it's perfectly consistent with the observations, which don't have any data down here, okay? So maybe that's a bit of a bummer. Maybe you wanted something that was very different. Or maybe it's good because at least our starting point plot still fits the data. So let's extend this now. And what I'm going to show you are some mass functions, I think, or luminosity functions. So here's the luminosity function from merger-driven growth of the galaxy population. Now remember, we grow black holes to turn on AGN to quench star formation. That plot I showed you of the line when you didn't have feedback mechanisms at the high mass end and when you did, okay? So the merger-driven growth builds a black hole population and that leads to the quenching. So if the black hole population is growing or evolving differently, that may affect your quenching of star formation in massive galaxies. So this is the merger-driven growth. And here's the disk instability-driven growth. So no difference really, okay? We're still looking for differences. We need differences to distinguish between these two models because they're very different. Okay, let's have a look at environment now. And what I've done is I've gone and measured environment for all the galaxies in the model and broken them into very underdense, which I'm calling void, the mean density, which would be the filaments, and cluster galaxies. And here are the luminosity functions for these different populations of galaxies. So here are the cluster galaxies, the mean, and the void galaxies. Okay, voids are sparser, so their normalization is lower. Okay, and this is this is our model. This is the merger-driven growth, and hopefully there's an environment dependence with the secular-driven growth or the instability-driven growth, because instabilities and mergers presumably happen in different environments, right? They're not the same thing, and yet without any calibration, they look very similar. Right? So this is what I would call a failure in some sense, because you're putting in new physics and you're looking for differences that you expect to find, and yet you don't find these differences. And we wanted those differences in order to inform the observers of what they should look at to discriminate between these two modes of growth. So it's difficult to discriminate between simple models of black hole growth using standard observables. So I've just used a couple of observables. Maybe we can find other observables. We need to use more refined observables, perhaps, to find these differences. Or maybe we just need a more sophisticated model of black hole growth. Okay, so that's future work. But it's a question we can ask that we can go and use these models to explore. And in this sense, I was very disappointed. I actually sometimes put a slide in here of someone looking very unhappy, because that's how I felt when I did this. I was expecting to write this beautiful paper, making these wonderful predictions using semi-analytic models. And I never ended up writing the paper. I mean, I probably still should have written the paper. Null results are still results. Let's have a look at another one. Evolution in the black hole bulge relation. Okay, so sticking with our theme of black holes. Now, this was a result that came about from a conference that I went to at Ringberg. So let me just tell a little story, okay? A story of me trying to scam my way through a talk. So I was giving a talk at Ringberg, and I presented a result. So this is the result. Okay, so here's the black hole bulge relation again. And I've just plotted it a little bit differently, and don't worry about the different colors here, okay, because this is a result from this paper. But at redshift 0, redshift's indicated here in the corner, okay, it fits on the relation. And again, don't be impressed by that. That was a calibration. Okay, so we set it up to do that. But interestingly, when I looked at this relation at higher redshift, I found this. And just focus on the blue points, right? Because the blue points are like a minimalistic version of this. The blue points lift off the redshift 0 relation. And even you can see it by redshift 1, but by redshift 6, it's kind of significant. And the data, we had no data for this. And I thought, awesome, right? We're making a prediction here that there should be evolution in the black hole bulge relation. So this is great. These models are making a prediction. And I gave this talk at Ringberg. I showed this result. And to be honest, at the time, I didn't really understand why the model was doing this. Because nowhere in the model do we put in any evolution with redshift into this relation. By all accounts, there should be no evolution. And so in this talk, I gave this hand-wavy explanation. I just bullshitted my way through it, right? And I mumbled a lot. Don't do that, okay? Because someone will corner you in a corridor and force the truth out of you. And those people were Hans Walter Rix and Eric Bell. And they hunted me down and they said, what you said there can't be right. That explanation, that's rubbish, right? Can't be that, blah, blah, blah. And finally, they got me to confess, I actually don't know why it does this, okay? But it was a challenge, right? Okay, you go away and figure out why the model's doing this, because I put no evolution into the model, okay? So a wonderful opportunity to explore something that's unexpected, okay? So that's what I did. And I figured out why. It's great. Okay, so let's look at the ways that black holes and bulges grow in the model. Now, this is just for the model, okay? But we're hopefully going to use it as some insight into the real universe. And we're going to consider the ratio, because it's really the ratio here that we're interested in. This ratio is lifting off. If the ratio stayed at 1, we would just sit at the redshift 0 result. But when the ratio changes with time, one is growing faster or slower than the other, then you're going to get evolution. Okay? So let's consider this ratio and look at all the different ways that black holes and bulges can grow in the model, knowing that nowhere in the model was there a 1 plus z or something that depended on redshift. And if there was something that depended on redshift, both the top and the bottom of this fraction both depended on redshift. So that was the confusing part. All right, so let's have a look. Okay, as the simple thing, when black holes and bulges grow, you'll have the progenitor black holes coming together and the progenitor bulges coming together, right? That's a growth channel. That's just through mergers. Okay, great. But the ratio shouldn't change. Okay, the ratio won't change. Okay, so no evolution there. Okay, so that's not what we want. As I said in a previous example, there's growth. And for the model that we have, this is just in proportion to the mass of cold gas that's there. So this is how a black hole will grow. But during mergers, there's also a starburst of new stars forming. And so the bulge can grow that way from a merger-induced starburst. But in the model, this is just in proportion to the cold gas as well. So even if the cold gas is strongly evolving with time, the ratio of these two contributions won't change. Okay? High redshift, you might have more cold gas. You're going to get more accretion onto the black hole, but you also get more stars form. And they both happen in proportion. So no evolution. So where is this evolution coming from? And I finally figured it out. And it's due to the morphology. Okay? When you get a merger, there's stars that exist in the disk that are disrupted and put into the bulge. Okay? But there's no comparable channel for growth through the black hole, for the black hole. Now, if this happened the same way all throughout cosmic history, then the denominator would just be a bit bigger, but the ratio wouldn't change with time. But if there was an evolution in how much mass from disrupted disks went into bulges, then you would get a changing ratio. So I went and checked this. And here's the growth rate from black holes. And here's the growth rate for bulges. Okay, and this is the ratio. And this is what you get from starbursts. And this is what you get. I'm just looking at what's going into the bulge, or actually what's going into the ratio here, right? And this is what you get from these disrupted disks. And you can see that actually there's this strong evolution for how many stars relative to the black holes go into the bulge from disk disruption. The starburst shouldn't evolve because, as I said before, when there's a starburst, when there's a merger or something like that, the bulge will grow in proportion to the black hole. It just all is in proportion to the cold gas. But this is a different channel. And this causes a change in the ratio in this model. And there's this evolution primarily because star formation increases to redshift 1. This is the McDowell plot. So stars are forming in galaxy disks. But in lambda CDM, the merger rate dramatically increases at low redshift. There's hierarchical assembly. Okay, so disks turn into bulges all the way down to redshift 0, and that accelerates beyond redshift 1. And this drives this growth here. And I had not expected that. And I don't think anyone had expected that at the time. And it came out of a model that had no evolution put into it. So models predict that there's an evolution in the black hole bulge relation, even when using an evolution-free description of black hole bulge growth. And this comes from the accelerated bulge growth. This is what was surprising, was that most people, when they see evolution in black hole bulge relation, they're thinking of the black holes, the evolution in the black holes. But actually, the black holes had nothing to do with this. It was the evolution in the bulge growth that drove a change in that normalization. And you can go out and look for this. And I still don't think the observations are good enough. It's kind of a minimalist model. Again, the observations are not good enough. But this has to be happening at some level if we think that disks disrupt and turn into bulges, which we're pretty sure they do. Okay. All right, let's have a look at another example. I don't know whether to do void galaxies. I want to skip void galaxies. This is a neat result, but I'll keep it in the notes for you. But I just want to talk about what's environment, because this was fun, and I'm kind of ending it on a warning. Okay, to be skeptical, especially you grad students. Don't be so subservient to your professors and all that you don't ask questions and you don't scratch your head and say, well, can you show me that? Can you prove that to me? How does that work? Okay, good scientists do this, and you should be learning to do that as a grad student. All right, so environment. If you're a galaxy person in particular, or go to some general conference, people will throw around this term environment, the environment of the galaxy. So what is it? Okay, so here's where I live in Melbourne. Okay, and this is my environment. Okay, and you can see I'm really close to the beach. It's awesome. Love it. Except at the moment when it's winter. All right, when I was in Berkeley, this is where I lived. Somewhere down here on Josephine Street off Shattuck, blah, 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 right? Now, except for the beach, right? It's kind of a similar environment, right? Okay. When I lived in Munich, here's where I lived, down here. It's a very different environment, okay? So this could be one definition of environment, okay? A sort of a large-scale environment. What's around you? And especially when you're talking about houses or places to live, this definition of environment is very, very important, right? If you're living in Munich up here in this environment, you're going to have a different life in some sense, or a different experience every day than if you're living down in this mess in Berkeley, in the US, or in Melbourne, right? However, in Berkeley, I lived in a house that looked remarkably like this. Okay? I don't live in a house that looks like this in Melbourne, but people do, right? This is a different kind of environment, okay? Again, very relevant to your lifestyle and how you live, but it's a different kind of environment that's somewhat decoupled from the definition that I just gave. Now, if you're Karen or maybe Claudia, right? This might be your environment. Am I right, Claudia? Yeah, good. Okay, the party is moving over to Claudia's after this lecture. All right, so another definition of environment, okay? Very different. And this might be halo. Some people use halo when halo mass is environment. Some people use some measure around the halo on a different scale as environment. And there are bucket loads of ways to characterize this, okay? So here's a couple. Group finders, closed pairs, nth nearest neighbor, halo mass, clustering, fixed aperture, so on and so on, background density field. And my concern was that we go to conferences, and because these are all represented on our graph by delta, that we put the delta onto our figures and forget about how environment was measured, and we compare results. And I was at a conference where, on environment, where people were doing this. They were just putting results from all these different measures and putting it on the same plot and comparing results and inferring things about the physics and the significance of environment and all this, and comparing different galaxy populations and so on. It was driving me crazy. So we started this project, and here's a list of all the participants. We wanted to get as many different environment measures as we could together and let everybody measure environment. And then we're going to compare them to see how they look. Okay, and this is a warning to you all to be skeptical. So here's a mock catalog that we made. So again, this is highlighting the uses that these mocks have. Now, this was a slightly different catalog. This wasn't a semi-analytic catalog where we attempted to model the physics. This was a HOD catalog where we imposed properties. And specifically, we imposed the correct clustering. We imposed the correct mass function or luminosity function, the right luminosity function by color, which is shown by the lower right plot here, and the right color magnitude diagram. So we statistically imposed that onto this population. And we had halo information as well. And we had the dark matter density information. And we let everybody go and measure environment, and then we compared. So here's one of my environment measures. And on the y-axis here is our, I guess let's call it our gold standard for what's environment. This is just the Gaussian smooth density in an aperture of 5 megaparsecs around the galaxy / halo using the dark matter particles. Right? That's the y-axis. And on the x-axis, I'm measuring environment for the same objects using a top hat sphere where I'm counting galaxies. So this is how you would do it in a survey. And I'm just taking an 8 megaparsec volume around and counting galaxies and then getting an overdensity, basically, where 0 is the mean density. Okay? And this is the correlation I get. And that's fine because we don't expect the dark matter. We know the dark matter and the galaxies are biased with respect to each other, so we don't expect it to be 1-on-1. But what do other environment measures get? So this is a top hat measure of environment using the galaxies. Here's Ivan Baldry's nth nearest neighbor method. All right? And you can see the y-axis is the same now. It's just the x-axis that's changed. It looks totally different. And yet people would compare these, a galaxy of the same environment, and compare the results that they get, which is not good. Right? And I could go through all the different statistics we measured. We measured like 10 or 15 different environment measures. They all look different. So why does this matter? Here's the halo mass function. So halo mass is on the x-axis. But I've broken it into halos that host red galaxies, red central galaxies, and halos that host blue central galaxies. And you can see if I use environment, not host red and blue, that are the most dense and least dense given the environment measure. Right? And you can see this is my environment measure, and this is the Baldry environment measure. Okay? And the red population, or the most dense population in particular, is very different. This is the group scale. So if you were doing, if your study was using environment to understand groups, maybe groups near clusters or whatever, you would come to very different conclusions. You would be using a different population of galaxies here, depending on the environment metric that you used. Okay, so ask questions, especially when people are not clearly defining the methods that they're using or comparing different methods that may not be comparable, even if the language that they're described in is the same. This figure just shows, again, the most dense and least dense, where environment is characterized by dark matter to work out those 20%, or halo mass to work out those 20%. And what's nice about this is what we already know, is that halo mass correlates with galaxy color. Right? I'm plotting the color here. Okay? And these red lines are the most dense. So most dense environments in the real universe typically have the reddest galaxies. And so this is where it's characterized by color, whereas dark matter doesn't correlate at all with the galaxy color. Okay, the distributions for the densest and the least dense are the same. So we knew that already, that dark matter halos are biased traces of the underlying mass distribution, where the underlying mass distribution is characterized by the dark matter here, and here we have halo mass. But we can look at this for the galaxy populations, and even though we find that both split nicely into bimodal, the nth nearest neighbor gives a better job of producing this red population. Okay? So again, depending on the science questions you're asking, you need to understand the methods that are being used. And this is especially important if you're passive in this process, that you're in a conference and you're listening to people present results. Put up your hand and ask, did you check that? Or how does changing this affect that? And these models are wonderful ways to check, right? To compare. They don't have to be right, the models, they just have to be fair and built in a way that's transparent and understandable, so that with that baseline, you can look at. So the take-home point here, not all environment statistics are the same. They often measure different things, and be wary of anyone who claims otherwise. Ask to see the details, okay? And we published this in this paper by Stuart Mulvey down here. All right. So hopefully I've given you a sense of a couple of the applications for these models, that they're not meant to just be a mirror image of the real universe, but they're just meant to be tools. They're tools to understand the universe. I've described the basics of how galaxies are built and evolve. And when you go to conferences, hopefully now when someone says, here's a semi-analytic model, you have some idea of what went into building that. And that hopefully will inform how you process the results that they claim, okay? For the better or for the worse. I talked a little bit about data access and delivery. I showed you Tau, but there are other virtual observatories out there, so please go and use them. Go and take advantage of all the hard work people are putting in to make these data products easily accessible to you and use them in your science. And that's the observational data sets and the theoretical ones. And then, especially that last point about environment, but hopefully you get a sense of the limitations of the galaxy models, why you would want to build a galaxy model, why you would want to run a simulation, and how you should always be skeptical about what's claimed for them, using them. But also the power that they can, and the insight that they can bring if you pose your question fairly and clearly. All right, and with that, I think my time is done. Let me say thank you. I'll put up these links again. Here's a link to Tau as well if you want it. Again, if you're interested in running Sage and having a go at that challenge of getting the mass functions right, just drop me a line and let me know. The tree files can be found here, but I think Karen is going to make available. And with that, let me finish and say thanks. So happy to take any questions.
Yeah, thank you very much, Darren. So do we have any questions in the audience?
About the correlation between the black hole and the bulge, how do the simulations deal with the bulgeless galaxies?
Can you just repeat the last part of that?
Okay.
How do the simulations
how do the simulations deal with the bulgeless galaxies?
The bulgeless galaxies?
Yeah.
Ah, interesting. They deal very nicely with them. And by that, I mean, so you can ask the question, where do bulgeless galaxies come from? So presumably a bulgeless galaxy has to have a very quiet merging history, or there has to be some mechanism that takes the stars in an existing bulge and flattens them back out into the disk. Now, for that later point, I don't think we really know of any mechanism, and in the simulations that get run, it's very difficult to produce a mechanism that will take an elliptical galaxy or a galaxy with a bulge and then take those disks, push them back out into the disk. Take the stars in the bulge and push them back out into the disk. So let's eliminate that and just say that if you're getting the evolution of the dark matter halo correct with the cosmology, and you're coupling the model and your merging model in particular and your secular evolution model to that dark matter halo history correctly, then you should be producing bulgeless galaxies in very low abundance, but you should be able to find them. And we do find them. I think there is a challenge in the simulations and models that you don't find them enough, and understanding the details of their formation is still somewhat of an open question, given that lambda CDM is a very dynamically evolving cosmology. So how do you dampen down the effects of the collisions of halos and the growth of large-scale structure such that it doesn't impact the stellar disk at such a significance, with such a high level of significance? But we produce them, and we produce them in the models as well. But I think it's still a bit of an open question.
More questions?
Hello. Is there any way to constrain cosmological parameters looking for these models? I mean, you said that we have to know about, to use a cosmological model to, not a cosmological model, but a cosmology to make the models. But is there any way to have some parameters free to try to constrain some of them? I don't know.
Sorry,
Do you understand?
I couldn't hear the question at all. Could someone closer maybe repeat it? I think it was how do you, is there a statistical way to
I'll try.
constrain the models? Is that a...
Okay, I think it was not too loud. Yeah, my question is if there is a way to constrain cosmological parameters using the model, because I know that we have to, as you said in the last presentation, that we have to use a cosmology to make the model. But are you listening? Just to.
So is there a way to use the models to constrain the cosmology? Is that the question?
Yeah, maybe to free some parameters and try to constrain.
It's a good question. It's a really good question. Actually, one of the things you do as a professor is spend a lot of time writing proposals to get money out of people. And if you're a successful professor, and I'll put that in quotes, then usually that means you've been able to get lots of money out of governments or other funding agencies to do your science. And one of the very popular things to ask, to investigate is exactly this question, is discriminating between different cosmological models, and in particular different dark energy models, because we measure the effects of dark energy, which we quantify in the standard vanilla lambda CDM model, but we don't know what it is. And so there are lots of different physical models that look like lambda CDM, but have a physical explanation for why the universe looks that way. And a popular thing to put into these funding proposals is to say, we're going to run n-body simulations of these different cosmologies, and then we're going to build galaxies on top and look for observables that distinguish between them. And I've written proposals like this, and it's something you have to try and do, but it's very difficult because, as I hope I've emphasized, is that there's a lot of uncertainties in the models themselves. And there's a lot of freedom to adjust things, to calibrate, and so on. So how do you know that a difference comes from the cosmology and not from just an assumption that's within the model? So for these methodologies, I think it's very difficult to distinguish between cosmologies. For other models like subhalo abundance matching or halo occupation distribution methods, they're more statistical and much more transparent, and they don't attempt to model galaxy formation physics. They just imprint statistically the observations on top. And I think because they're a little more transparent, they're more limited in what you can use them for, but they're more transparent, and they might offer more hope, I think. But it's a good question.
Thank you.
I hope I answered your question.
More questions?
Yep.
Do you hear me? The secular and the merging driven mode.
Yep.
And I have two questions. Those was very interesting. Do we think there is any hope that we can use available data, but I understand that high redshift is difficult, to try to discriminate one of the two? This is the first question. Yeah.
You're saying, do we have high redshift data that can maybe discriminate?
So high redshift we don't have much, but maybe below redshift 1.
Yeah. So maybe if we extend these results out to high redshift, we'll see a difference.
The problem there is to get them black hole masses is really complicated. So I don't know if you would trust any observation there.
Yeah, you're right. I focused on redshift 0 because this is where we have the best data. But you're right, looking out the high redshift, and there are other statistics I could have looked at, like the black hole mass function, for example. We now have data on that. At the time, the data was pretty crappy. The quasar population, there's a whole bunch of them that we could potentially examine and maybe flesh out the differences. And I didn't do this in this study. But But definitely going to high redshift is what I think you want to do.
Good. Thanks.
Anyone else? So I actually have one question, and it's related to what you said at the end of the talk, comparing different measures of environment.
Yeah.
So my intuition is that even if you think of one individual measurement, for example, the nth nearest neighbor,
Yeah.
that's going to be highly subject to the depth of your survey and other problems like how you deal with the missing satellite problem, because that's going to put a lot of different smaller galaxies in there. So do you think that's a different problem as well that might further enhance how we understand measurements of environment?
No, it's definitely a challenge. So, I mean, let me just say up front that there is no one measure of environment. It would be nice. There's one word, environment, and we all use that one word, but there's no one measure. It would be nice, like there's one halo mass function. There's not like 5 halo mass functions. There's one halo mass function. There's one 2-point correlation function, but there's not one measure of environment, unfortunately. And so we just do the best we can. With the observations, measuring environment with the observations, like most observational studies, requires a lot of corrections and compensation for things. So you have to understand your selection and your selection function. You have to understand, you have to try and correct for missing galaxies, fiber collisions, for example, the survey depth and the integration time, the apparent magnitude limit, as you were saying. But these are all things we can get a handle on, I think. Observers, and I've done these studies as well. Observers are really good at quantifying these things and correcting for it. And at least where they can't correct for it, they limit the catalog so that it minimizes those effects. And then hopefully they'll fold those residual effects into their discussion of the significance of their results. So it's an important point, but one I think observers are pretty good at quantifying and understanding. I just want to make another point with environment, and that's that I'm always a little bit dismayed when, so the 2 most popular environment measures are this nth nearest neighbor and fixed aperture. And nth nearest neighbor just means take your galaxy that you're interested in looking at the environment for and find the 5th nearest neighbor away. How far is that? That gives you a number, like a distance. And that quantifies your environment. So if you're in a very empty region, that number is going to be large. You're going to have to go a long way from the galaxy to find the 5th nearest neighbor. So large values reflect very sparse environments. Whereas if the number is small, then you're in a dense environment. So that makes sense. Whereas fixed aperture, it puts exactly what it says. It puts a fixed volume. It considers a fixed volume around the galaxy. Okay? And again, you'll get an environment value for this. How over or under dense relative to the mean is that? And if there are no galaxies in there, then you're obviously in a void, or if there's only one. But if there are 100 galaxies in there, then you're in a very dense environment. So again, makes total sense. The problem is the nth nearest neighbor environment measure is scale dependent. Okay? Very underdense environments, delta, relative to mean, they're really probing very large scales because you have to go a long way away from the galaxy, 5, 10, 20 megaparsecs away. Whereas fixed aperture is fixed scale. So if you're using these environment measures to explore the physics of galaxy formation, if you take a void galaxy measured from nth nearest neighbor and a void galaxy measured from fixed aperture, you're actually examining totally different physical scales, the physics on different scales. And so again, it's a warning that these things aren't doing the same thing. They're not measuring the same thing. And whatever conclusions about the physics of galaxy formation for, say, void galaxies that you come to, not necessarily going to be the same for void galaxies identified using nth nearest neighbor, which might probe 20 megaparsec scales, to fixed aperture, which might be a 5 or 8 megaparsec scale. So again, it's very important. You have to correct the observations, but even when you've corrected the observations, the method that you apply to that makes a big difference as well.
Okay, thank you. No more questions. I see no hands. So if not, let's thank again. Let's thank Darren again.
Thanks, guys.
And thank him for the class. He won't be able to give another class, so let's thank his whole appearance here at the school again. So thank you, Darren, for making the effort to be here in virtually, I mean.
It was my pleasure. I hope you get a lot out of the school.
Well, so we have perhaps a few announcements. I think there's only one main announcement.